Okay, for our next example, our last example from section 3.4, I want to do this problem of the points. You can read about this in the book too. So here's the idea. A series of games are played between two players. We'll call them A and B. And we'll suppose the games are independent and the probability A wins a game is little p. Which would stay true for all the games. It would be little p, some number between 0 and 1. So the probability B wins a game is 1 minus p. We also suppose there's this overall match, which is 1 when either A or B attain a particular number of wins. Okay, and suppose additionally, and suppose A needs n wins. You're at this current state in the match where A needs n wins and B needs m wins at current time in order to win the match. You can think of team sports, for example, the NBA playoffs. Currently, Boston and Miami are playing to see who's the first to win 4 games are. Currently, Boston needs 3 wins and Miami only needs 2. So this would apply to computing, say, the probability that Boston wins the match. Okay, so this is the type of problem you could apply it to. All right, well, I could go on and describe it in a general way, but I think this would be rather difficult. So actually, let me put in a real example here, and then we will go back at the end and sum it up. So here's an example. Suppose for the rest of the games between B and A, suppose B has a 2/5 chance to win and A has a 3/5 chance to win. Okay, this is pretty bad for B. So let's suppose n, the number of games A needs, we're going to model it after the current state of the basketball series, but it might be different by the time you read this. So A needs 2 more wins, M equals 3. B needs 3 more wins to win the series. And we'll suppose A team has a lower probability to win. So I'm going to make it, should we make it 2/5? 0.4? Yeah, we'll just make it 2/5, even though it should probably be closer to 1/2. So the probability B wins a game is 1 minus P, right, is 3/5. Okay, so find probability. Let's do B because we're in Boston. So probability B wins. So what's the probability of the team? Let's do A because A is defined as P. So let's do probability A wins. Probability Miami wins. Okay. All right. I hope I'm not confusing you by mixing these two examples up. I have 2 players. One needs 2 more games to win. The other needs 3. But the player who only needs 2 more has a lower probability to win each game, right? All right, so one approach, probably with a very small number like this, a reasonable approach is to list the ways A can win. So let's try listing. Let's try to list sequences in which A, and these are also intersections. Okay. Well, one is A could just win the next two, right? That's certainly one. And I'll put little subscripts down here for the remaining games. Okay, what else could happen? Let's see. A could win the first one. Then B could win the next one. Then A could win the next one. That could certainly happen, right? Okay, what else? A could win this. B could win this one. B could win this one too. But B can't win the next one because then B would win. So then I have A form. What else could happen? B could win this one. B could win this one, right? Then A could win this one. A could win this one. What else could happen? B could win this one. A could win this one. B could win this one. A could win this one. All right, let's see. How many others are there? This is getting ridiculous. So B could win this one. And let's see. B can win two, right? So B can win this one. And see what I mean? It's hard to even list something this small. B could win this one. B could win this one. But now A has to win the next two. I think this may be it. Right. You see how it's a little complicated, okay? So we can try, I think this is it though. Does anybody disagree? So the number of ways A can win two. Can win this one, this one. Once I start thinking and going slow like this, the time goes really fast. So A could win these two. A could win the first one, lose the next, and then win the next. Is there any other way A can win in three? Yes, A can win in three this way too, right? So there's no other way A can win in three if A wins the first, though. It has to be like that. So I do think this is those ways. Now in four, there are more ways. There's only three more ways for them each to win two. But let's see. I think this is going to do it, though, because what are the other two? All right, well, you can see already it's kind of a mess. Let's assume this is right, and let's compute these probabilities. So the probability of this, so let's make a table over here to save room. The probability of this one, remember A, we can just use P, I think. A is P. So here I have P squared. I'll fill it in later. Here I have P squared, 1 minus P. Here I have P squared, 1 minus P squared, right? And here I have P squared, 1 minus P. Here I have P squared, 1 minus P squared, and P squared, 1 minus P squared, right? So those, if I add these up, they're all mutually exclusive. I add these up, I should get the correct number over here, okay, for what it is. So if I add them all up, I get P squared. And if I factor the other terms, I get 1 plus 2, 1 minus P, plus 3, 1 minus P squared, right? That's what I get there. Okay, so that's the sum of those. And we should get some number there, okay? I can just put in what I get. So if I put in 2/5 here, what do I get? I get 2/5 squared. And here I get 1 plus 6/5 plus 2/5, so I get 3/5 squared, that's 9 25ths. I get 27 25ths. Here I get 30 25ths, so I get 57 25ths. I get 82 25ths. So I have 4 times 82 over 625. This is 328 625. Now, I'm a little concerned. I'm sure one of you watching probably realizes that this is wrong. I couldn't even tell at the beginning. So I have my number here for this. And maybe this is a mistake to let this go on this long. It looks pretty good. I mean, it looks pretty right? It looks like a little more than half, but that makes sense. So I think I have to go on to the next video to finish this problem. So let me do that, and I will see you on the other side.